everyone, thank you so much for clicking onto the video. Today we're going to be learning about different effects on the rate of reaction. So first we're going to look at temperature, and we're going to define the term of rate of reaction and then look at the effect of temperature using the Maxwell-Boltzmann curve. And then we're going to look at the effect of concentration and pressure. And then we're also going to look at the effect of a catalyst, and we're also going to use a Maxwell-Boltzmann curve as well. We're then going to use a required practical to further your own understanding. So we're going to use the investigation of how the rate of reaction changes with temperature. The definition of rate of reaction is just the number of successful collisions per unit time. So different factors can affect the rate of reaction, and we're going to go into more detail about that a bit later. What happens when we increase the temperature? Well, this is the normal Maxwell distribution curve, and if we increase the temperature, then a few things happen. So number one, all the particles are supplied with more energy. So all the particles gain kinetic energy. And this means that because they gain kinetic energy, more of them actually possess the activation energy required for a successful collision. More of those have the activation energy required. And so that means that a bigger proportion of them will actually have a successful reaction. Now, a smaller point is that if you increase the temperature, the particles will move more. So there's actually more collisions per unit time. So we have more collisions. So that also increases the amount of successful reactions per unit time. So then the new graph would look something like this. So basically what happens is that the activation energy here has stayed the same, but the number of particles which possess this activation energy has increased because it's this area under the curve here. It has increased from this little tiny section here. So this is the number of particles possessing the activation energy. And we see that this most probable energy has also changed. So it's changed to about here. Another thing to note is that the areas of the graphs should be the same because we're not altering the number of molecules. We're simply just giving them more energy, basically, by increasing the temperature. So the three things you need to remember are that when we increase the temperature, the particles gain kinetic energy, so there are more collisions per unit time, and therefore more of the particles collide with each other, and also more of the particles then possess the activation energy required because they get more energy from the rising temperature. So overall, there are more successful collisions. And the two things you need to remember about the distribution are that, firstly, the activation energy doesn't change, but the number of particles possessing the activation energy is increased, and also the most probable energy is increased. So what happens when we increase the concentration of the solutions? Well, if we have the solution, so let's just say we have, for simplicity, we have a box and we have all the particles. Well, if we increase the concentration, we have the same size of box. So this is normal. This is increase the concentration. but we have more particles in that space compared to before, because that's what concentration means. So concentration is normally measured in moles per decimeters cubed. So this is the symbol for concentration, and this is normally measured in moles per decimeters cubed. So that means how many moles of the substance do we have per decimeters cubed, which is a volume. So it's moles over the volume. So it's basically how much there is in a specific volume. So this volume is the same as this volume, but this one has more particles in compared to this one. And that's what we mean when we increase the concentration. So in terms of rate of reaction, when we increase the concentration, because there are more particles, that means there are more collisions per unit time, because if these are all moving about, then these will collide more with each other compared to these ones, because there are more of them. And so the rate of reaction increases when we increase the concentration. And that's because if there's more collisions per unit time, then there is a higher rate of successful collisions per unit time. Now we're going to discuss what happens when we change the pressure of gases. So when we change the pressure, we're basically changing how packed the particles are in a specific space. So another way we can think about it is if the pressure increases by double, then the volume decreases by a half. And this is stated by Boyle's law. And Boyle's law states that pressure, which we'll call big P, is inversely proportional to the volume. So that means that if we double the pressure, then we halve the volume. And so if we have a container with the particles, let's say we have 8 particles in this specific volume, if we halve the volume and still had 8 particles, then this pressure would be double of this one. So if we called this P, then this will be equal to 2P because the volume has decreased by a half. And so what this does for the rate of reaction is it increases it. And that's because there are more collisions per unit time. And so actually there are more successful collisions per unit time, which means that more of the particles will react with each other. And that increases the rate of reaction. So we're going to have a quick look at a continuous monitoring method practical. And continuous monitoring just means that you're taking, you're recording values continuously. So say every minute or every 2 minutes. So this experiment is when we add solid magnesium to dilute hydrochloric acid. And what is formed is, if we write out the equation, we have magnesium and hydrochloric acid. And what this forms is we form the magnesium chloride salts and hydrogen gas. And to balance it, we have 2 hydrochloric acids. The reason I know it's MgCl2 as a formula is because we have Mg2 plus ions and Cl minus ions. So the ratio is 2 to 1. So for every magnesium ion, we need to have 2 chloride ions, and that's why the formula is MgCl2. So we form hydrogen gas, and that's what we're measuring by using the gas syringe. So the amount of hydrogen gas should increase to start off with and then level out as soon as the reaction kind of stops. So what we do is we first measure out some hydrochloric acid. So it's normally 10 centimeters cubed. And then we place it into this conical flask. And then we set up the syringe and a stand. So we put this syringe onto a stand and connect it to this conical flask. And then we cut a small length of magnesium ribbon, so let's say 4 centimeters of a magnesium ribbon, and we fold it loosely in half. And then you add the magnesium ribbon to the hydrochloric acid, and then you have to make sure to attach the delivery tube, which is this tube here. You have to make sure that you attach that straight away once you've added the magnesium, so that none of the hydrogen gas which is created actually escapes and all of it goes into the gas syringe. And what we do is we record the volume of the gas every 10 seconds for 2 minutes about. And then what you should get after you get the results is when you plot a graph, it should look something like this. So you have the volume, normally measured in centimeters cubed using a gas syringe, and then the time along the x-axis. And you should normally get a graph that looks a bit like this. So at the start here, the rate of reaction is very, very quick. And this is because there's lots of magnesium for the hydrochloric acid to react with. But then as the reaction continues, the rate here begins to slow. And this is because the amount of magnesium is less, so less of the hydrogen gas is produced. So when it levels out here, then we know that basically the reaction is done. And so the way we work out rate is the volume over the time, because it's always measured as something divided by time. And in many rate experiments, a gas is produced, and so we often measure the rate in grams or centimeters cubed of gas produced per second. So in order to work out rate at different times, we would draw tangents. So we would have, if we were going to take this dot here, for example, we would draw a tangent. So at this time, let's say that's 2 seconds. Actually, no, we're taking in 10 seconds. So let's say that's 20 seconds. Then we know the rate at 20 seconds when we work out this tangent here. So we would do the difference in y divided by the difference in x to find this rate. And then you could do that all the way along the graph. So let's say we could do it for 50 seconds as well. So this tangent would look slightly different. It would look like this. So then we could work out the rate for that as well. So we can monitor how the rate changes throughout the experiment. So now we're going to talk about catalysts and how they affect the rate of reaction. So catalysts are substances that affect the rate of chemical reaction without being chemically changed themselves. So how they end up is the same as how they started, because they're left unchanged. So that means that we can reuse the same catalysts for the same reaction again and again. And catalysts usually speed up the reactions, so they're very important in industry, because it's a lot cheaper to speed up the reaction compared to using higher temperatures and pressures for the same result. How catalysts work is that they provide an alternative route where the activation energy required for a successful collision is decreased. So more of the particles actually possess this activation energy required, so there are more successful collisions per unit time. So overall, the rate of reaction increases. These are a couple of examples of real-life examples of catalysts. So I'm just going to quickly talk through the catalytic converter in car exhausts. So all new petrol engine cars normally have this catalytic converter, and they basically reduce the levels of polluting gases in the air. And so it's made out of a honeycomb, and it's made out of ceramic material and coated with platinum and rhodium, which are the catalysts. And the honeycomb shape actually provides a really large surface area, and so not much of the platinum and rhodium is actually needed to coat the whole thing. And also the rate of reaction is increased significantly by the increase in surface area. So as the gases pass over the catalyst, the polluting gases react with each other to form less polluting gases. So, for example, we could have carbon monoxide and nitrogen oxides. Both of these are polluting gases, and they can react together in this catalytic converter to form carbon dioxide gas, which is normally found in the air, and nitrogen. So these two less polluting gases are formed from two very polluting gases. And so that's how catalytic converters work. Another reaction that can happen is one between hydrocarbons and the nitrogen oxides. So we can have hydrocarbons, which are molecules with only carbon and hydrogen. So they only have carbon-hydrogen bonds. And when they react with nitrogen oxides again, they can form carbon dioxide gas and water and nitrogen, which are all less polluting to the atmosphere. So now we're going to look at what actually happens when we use a catalyst. So the first thing that happens is that we go through a process called adsorption. And note that it's adsorption. So what happens here is that the gases which are wanting to react, they actually form weak bonds with the metal ions of the catalyst instead, first, before they react with each other. And this makes sure that they're in the right position in order to react. So say we have a metal surface here, and this is the catalyst. And we have a gas incoming here and a gas incoming here. The weak bonds which form, they form with this metal surface, and this ensures that they're in the right place in order to react with each other. And so then they react on the surface of the metal, and then desorption occurs. And what this means is that the products then break away from the metal atoms, and this frees up room on the catalyst for more gases to take their place and react. So from this metal surface, this catalyst, we then have this which exits. And this means that these incoming gases have room to do the same thing, and not necessarily two gas molecules react on the catalyst. There's many particles reacting at the same time. So we've learned that catalysts speed up the rate of reaction by providing an alternative route with a lower activation energy. So more of the particles have this activation energy in order for a successful collision. And so we can apply this knowledge to draw the Maxwell-Boltzmann distribution for it. So if this is our normal distribution, and we have the number of particles or molecules, and this is the amount of energy. If the graph normally looks like this, with the most probable energy over here, and the activation energy over here, then we can work out how the graph changes for the addition of a catalyst. So the first thing we know is that the activation energy decreases. And so we can change the position of the activation energy on the graph. So let's say the new activation energy is here. And the other thing we know is that the number of particles doesn't change. So the number of particles remains the same. And also, the most probable energy doesn't change either. So the most probable energy also remains the same. And so from these 3 points, we can actually just figure out that the graph doesn't change at all. The graph looks exactly the same, but the only thing that has changed is this activation energy here. We've moved it back. So there's more of these molecules have the activation energy, but the entire graph hasn't changed. It's just the activation energy which has moved to a lower energy.